So I'm now having a problem with the meaning behind the statement right here. Because as of now, we only have an intuitive notion of what this really means. And our intuitive notion is the following. As x approaches a from both sides simultaneously, the y values, if this is a true statement, are approaching L. Now, remember, I don't care what the corresponding y value is when x is a in evaluating such a limit. Again, I have this mathematical blinders on. When I'm trying to evaluate a limit, I don't really care what's going on when x is exactly equal to a. I only care about what I expect the y values to be as the x values get closer and closer to a from both sides simultaneously. So if you don't mind, I'm going to take this to the next step. I need to have a rigorous definition of what this really means. And historically speaking, this is not an old definition. This is fairly recent in the history of mathematics. So here I go. I'm sorry, I need a couple colors. I hope my red's not too vague or light on the board. For this to be true, it means that no matter how closely I deviate from L up and down, in other words, if I deviate from L epsilon units above or epsilon units below, is the red showing up? Oh shoot, it's a little tough. That's an L plus epsilon, L minus epsilon. Where epsilon has to be strictly positive, and typically speaking, it'll be very small. For this to be true, it means that no matter how far I deviate from L, say epsilon units above or below, then I'm guaranteed x1, x2, then I'm guaranteed that's the amount of deviation from A to the left to the right, say my delta units. That guarantees me y values on the curve that are within epsilon units of L. Now let me say it one more time more continuously, if I can use that word. For this to be true, it means no matter how small epsilon is a positive number, in deviating from L by epsilon units, I'm guaranteed there's a corresponding delta deviation from A that guarantees me that the corresponding y values are within epsilon units of L. There's my verbal description of my rigorous definition. I don't like how it's verbal, so if you don't mind, I'll put it in terms of mathematical symbols. So here I go. If this is true, it means for all epsilon greater than 0, there exists a delta greater than 0 such that the absolute value deviation between f of x and L is no more than epsilon units whenever and absolute values x minus a is no more than delta units. Sorry, I've got my eraser. I think this is so important. I don't want to be scrunched up over here. I'm not going to change anything, but let me make my word whenever smaller. Now, I got to confess, sometimes I don't like using the word whenever. Sometimes I convert this to an if-then statement or a conditional statement. So I guess I can rephrase it by saying if this is true, then this is true. So everybody, a couple things. Number one, I know I'm using some new symbols, or I assume they're new to you. I'm not making up these symbols out of thin air. These are standard symbols we use in symbolic logic. When I use this uppercase A, I sometimes refer to that as my universal quantifier. Now, this universal quantifier stands for the phrase for all or for every. This uppercase backwardly written E is my existential quantifier, and it represents the phrase there exists or there is. I'm sorry for this notation, it's a habit of mine. If you see a backward C, a horizontal line through it, 2 dots on either side, it just stands for the phrase such that. And one last thing before I get rid of all this. Remember, we're dealing with limits. And so when it comes to limits, I don't care what the HECK happens when the x is exactly equal to a. So I have a tendency to stipulate that. There is my formal definition of the limit.